Okay, so page 31 in the workbook, chapter 9. It's not on the test. It's going to be on test 3. It's the first material that's on test 3, but we got to keep going. Let me click this as it's done buffering. Okay. So this chapter is going to discuss momentum and center of mass. There's a lot involved in this chapter. One thing that's significantly different in this chapter than everything we've done previously is we're going to finally start talking about things hitting on a regular basis, impact, collisions. So involved in momentum, usually momentum is used to handle problems with collisions. Now, if you think back, we've only had a few collisions, and usually they were collisions of a block hitting a spring, right? But what about two blocks hitting each other? In order to really understand this, we're going to try and learn about this concept of momentum, all right? And then instead of just analyzing blocks moving around by themselves, we can talk about blocks moving around by themselves, then impacting other blocks, then moving around, and it adds another tool to our kit. And if you think about it, I guess from a big picture, kind of a review of the semester, you can think about the different topics that we've discussed. Kinematics, force, energy / work. And this next one is the last piece of the fundamentals. Okay, these are kind of the 4 fundamental things you should learn in a beginning physics course. If you know these tools really well, you can pretty much learn anything else in physics. Now, to be clear, you need a lot of practice with this stuff. And one of the first things we do in chapters 10 and 11 is we take these 4 topics that we spent 9 or 8 weeks on, and we're going to redo them again in 3 weeks, but add in rotation. So maybe a hidden thing that's not seen here is rotation. So we're going to have to do these all again, rotational equivalence. More on that when we get there. So this is, I guess, a big fundamental topic that I want to make sure you understand deeply. All right.
So like torque?
What's that?
Like torque or?
Yes, the rotational equivalent of force will be torque. We have rotational kinematics, we have rotational kinetic energy, and we have angular momentum. So those are the topics that we're going to discuss in chapters 10 and 11. So just imagine how tough that's going to be. Redoing 8 chapters in 2 while making it more complicated and adding in a lot of cross products. Yeah. Believe it or not, we've been working really hard to set you up for success in those. So more on that, we will be doing torque then. All right, so let's start with some definitions. You've got your notes there. If I write something that's not in there, maybe you want to talk about it. Momentum. We're going to use the symbol lowercase p, lowercase. It's a vector. For non-relativistic particles, or, well, let's just leave it at that. Most of the time, we're going to say momentum is mass times velocity. So an object's mass times its velocity will be its momentum. All right? There's going to be collisions. So I want to mention, usually, I'm going to use the collision time as a small time interval, a delta t. So when I'm talking about a collision time, I'm going to use a delta t, not a t. All right. Average force. It turns out, how did I want to say this specifically? This one I'm being a little bit careful. The force of, to make it match, what did I say? 1 on 2? Of 1 on 2. So we're exerting a force on 2. That's what I wanted to emphasize here. When you exert a force on 2, it changes the momentum of 2. Okay? I know that seems simple, but we could also write this as a derivative. Okay. It turns out this is tremendously useful in coding. Okay, we're going to use this trick all the time in coding towards the end of the semester. Basically, if you have a known force and you know a small period of time, you can multiply the force by a small period of time to get the change in momentum, right? If you rearrange this, you can get the change in momentum, which that's why oftentimes we'll see this extra term, impulse. Now, different people use different symbols. The one I'm going to use today is J, vector, capital. All right. So impulse is J. It's a vector. It has to do with the change in momentum of a single object. Okay. So for example, this marker, I can produce an impulse on it and change its momentum, right? I changed the marker's momentum. There was impulse on that marker. I better get that because that seems to be the only red today. Okay. All right. And then I know I already mentioned this, but just kind of, if you look up here, and I should be careful here, we wanted to clearly denote that this was average, so maybe I'll write average right there. Notice, this is what I was saying. Impulse is force times a change in time. And I guess we could talk about this in two ways, and hopefully I don't break the computer again. I'm hitting out my paper towels. I want you to think about two collisions here. Ready? Watch. We got this paper towel roll, and I've got this piece of paper. Oh, if I could actually hit it. It's tricky. I don't know if you can see this, but when I hit the piece of paper, it stays with my hand for a little bit. If I could actually hit it, there. The idea in this is think about the collision time. With the paper towels, there was a very short collision time, right? So if you could change the collision time to make it longer, you can get less force. Got that? So I could try to punch the paper just as hard as I try to punch the paper towels, but the paper tends to give. It elongates the collision time and it reduces the force on my hand. All right, anyways, just think about that. Or if you're bored after class and you have some eggs to waste, you could imagine doing this. Have somebody throw you an egg and try to catch it with your arm outstretched right in front of your face. What's going to happen if somebody threw an egg at my hand as hard as they could? But imagine if they threw it at a giant bed sheet, right? The bed sheet would give and then the egg might not crack. Same idea here. There's a force time trade-off, so to speak. Okay. The longer you take for a collision, usually the less force involved. All right. So far, so good. Dom, anything you want to say about it? Or do you want to throw an egg?
I'll throw an egg at you. The longer the collision time, the smaller the acceleration, thus the smaller the force.
So what Dom says is longer delta t implies smaller acceleration and smaller. Did I get that right? What you said, Dom?
Smaller delta b over delta t. smaller. Yes.
All right. Now, where this gets tricky is when we start bringing in Newton's third law. Clean these glasses for a second. And I think, make sure here. I'm going to talk about this on page 32. I've done a derivation for you on page 32. So if you could turn to page 32, that way you can watch what I'm doing on the board and not have to write anything down. Okay. So on page 32, I want to take a little extension of this. And I'm going to write it on the board too. Come on now. Oh my gosh, is this one of those days? There it goes. Okay. All right. I want to start with Newton's third law. Whoops. Now you know Newton's third law. I'm going to write it like this. The force of 1 on 2 is equal and opposite to the force of 2 on 1. If I push on you, you push on me the same amount, but in the opposite direction, right? Well, now we can rewrite this in terms of momentum, okay? This is on 2, right? So this must mean the change in the momentum of 2 over some collision time has to equal the negative. Let me make that negative 5 so I don't forget it. Now, to be clear here, we're talking about two objects. Imagine they're deep in space and they're the only two objects in the universe and they're pushing on each other. Now, clearly, we're assuming these things are hitting each other and they're going to exert forces on each other. So I just want to make it clear that the time that 1 is touching 2 should be the same as the time that 2 is touching 1. Do you agree? Two objects are going to be touching for the same amount of time. That's why I didn't put subscripts on the time, if you're wondering. Now, because they collide for the same amount of time, that's going to drop out. And now I'm going to rearrange this to the other side. Change in momentum of 2 plus the change in momentum of 1 equals 0. Or change in momentum of the system. Because remember, we only have two objects in our system here. 1 and 2 are the only things in the universe. 0. That's almost like saying the initial momentum of the system must equal the final momentum of the system. Do you agree with that statement? Take a second to think it through. If the momentum of the system doesn't change, its initial and final states must be the same. That is a conservation law in physics. Remember? When we had conservation of energy, E initial equals E final. Now we see that momentum is also conserved. Kind of cool, right? In practice, what would this look like? Keep in mind, there's both 1 and 2 in here. I'm going to write out an equation for you here. Mass 1, velocity 1 initial vector plus mass 2, velocity 2 initial vector should equal mass 1 final plus mass 2 final. Take a second to absorb that. Do you agree with that? This is the initial momenta. These are the final momenta. Now check this out. Why is this cool? You remember when we had me punching the paper towels and all these things? I don't have a scale to register the force in my hand. It's difficult for me to say, oh, that was exactly 3.28693 newtons, right? I can't do that. Now, maybe with advanced technology we could, But one of the things that's really cool about this is if you know the velocities of two objects before the collision, and you know one of the velocities afterwards, maybe through taking a video or something, we could figure out the fourth term, right? Or let's say we know all of the velocities from making videos, we could maybe figure out one of the masses of the objects, right? If I give you an example here, oops. Oh, geez. Sorry. It's so slow here. Okay. Forget about this thing for a moment. I can't move it, right? But the idea here is this. What if I have two objects? Now these happen to have magnets in them, okay? And so when they get close, if you watch carefully here, they should bounce off each other. Right? And you could put different masses on these. Like I could put one of these on here and I could put two of these on here. And the idea is we could have these collisions. Well, that's kind of an interesting one. But we could see if you put on different amounts of mass and they're moving with different speeds, we should be able to see different types of collisions happen. And we're going to come back to this one in a minute. But the idea, again, making sure that just stayed in there. Whoops. Oh, this is interesting. These magnets are not affected when we put all the extra weight on. Let me take some of this weight off. All right. Here's an interesting one. There we go. This is a wild collision. We see if two objects have the same exact mass, this is kind of like two pool balls. Have you ever hit pool and had the cue ball stop and the other ball goes flying off? When they have two objects with the same mass, one of them's initially at rest and one of them comes flying in. If the collision conserves energy, the initial one will stop. Okay, crazy, right? I'm just showing you an example here for fun. We can do lots of these different examples. What if they stick together? Right? These ones have Velcro on them, so they'll stick together better than these two here. We could have an experiment where a heavy object hits a light object. They stick together and they go sliding off. Or we can try it again, like this, where a light object hits a heavy object. And they're a little bit different. You can see there's different things happening. The one thing that's true for all of these types of collisions, whether there's magnets in there or not, is this. Momentum initial equals momentum final, and we get this result. So we say momentum is conserved. Any questions right now? That's kind of your big picture conceptual thing. Momentum relates to force and collision time, and we can also use this conservation momentum equation. Those are the two big pieces we're going to explore today. Got it? All right, we should probably do a problem to kind of see how this actually works out. I will mention before I go on, we're going to need some practice with this. But if you look at the bottom of page 32, there's going to be a strategy there. And then again, on page 31, there's all your definitions. So basically, when you're doing work in this chapter, pages 31 and 32 have lots of hints. Okay, great. Let's do 9.1. Okay, let's do 9.1. I'll erase the board and catch up. Two, I guess. Man, this board's getting worse. All right. Let's get into it. Okay, we've got a bouncy ball and it's going to hit a wall. In this case, there's a rock wall that's attached to the earth. You can basically think of that wall as part of the earth, right? It's embedded in the earth somehow, its foundation. And I'm going to label these before and after. You could label them stage 1 and stage 2. This is problem 9.1. We know the mass of the bouncy ball. What did I say it was? 0.0.
0.7.
Okay. Thank you. 75 grams. We know initially it's moving 6.0 meters per second to the left. Afterwards, it's what, 4? Yeah. To the right. And we're told it's a collision time of 0.05 seconds. Hopefully that makes sense what I mean when I say collision time. Right? The contact time between the ball and the wall is the collision time, the time that they're in contact. So 50 milliseconds. Now, when you think about that, this is not really that, these are somewhat realistic numbers, is all I want to say. Right? You could imagine throwing something at about 12 miles per hour and it bounces off at about 10. 75 gram ball, the collision is going to happen pretty quickly. It happens so quickly you could barely tell, right? So that's about right. Not absurd numbers. So now, part A. I want P initial of the ball. And I'm just going to use a subscript B here, P initial B. What is it? What was the equation for momentum? Do you remember?
Mass and velocity.
Mass times velocity. So what's it going to be? You can get out your calculator.
0.45.
What was it?
0.45.
0.45. What are the units?
Kilograms times meters per square second.
Yeah, don't overthink it. It's just kilogram meter per second. Did anybody else get that number? Why is he wrong? If you catch yourself, don't say it. See if they catch it too. Why is that not right? It's literally not right. It's left. Negative I hat. This is a vector. Oh,
Well,
yeah, fool. You got it?
Well, it depends on where you're
Oh, that's right. You were going the other, you had a flip coordinate system. My bad.
yeah.
Yeah, right. So unless otherwise specified, however, we assume a standard coordinate system of x to the right and y up. So we can see that it's useful to always have a coordinate. All right,
Because I have
good.
-4 for the
What's that?
I have -4 for that one.
Oh, this was -4.
No. Like my velocity for the after one's negative.
Oh, right. There you go. Okay. So is everybody okay with this? The numbers work out? Okay. So the big thing I was trying to catch you on there was what we caught. Remember, momentum, we have to start thinking about vectors again, plus minus. It's not the same as energy. Okay, P final. That's pretty easy now. What's that going to be? 2/3 of that? Is that 0.30? Right? Is that what you got? Yeah? I should get my calculator out too. I just feel uncomfortable without having it. So 0.075 times 4. Got it. Now, we're only doing 2 sig figs here. The numbers, is this correct? Strictly speaking, what should I also include? I have. Now, this raises a question. Remember when we did kinematics? When we did one-dimensional kinematics, we never wrote down I hat or J hat. Do you remember that? So a lot of times we aren't going to write down the I hat and J hat here, but I do want to emphasize you always have to think about the minus signs in momentum, just like we always had to think about the minus signs in kinematics. Is that good? Okay. Okay. C. What's the change in momentum of the ball? And we can see now those minus signs really matter. Do you agree? It's going to be final minus initial. What is it? Is it 15?
Point 1.5.
It's final
30.
minus initial, which is
So it's 0.75.
Oh, it's the
0.75, right? And that's what I wanted to emphasize. The change in momentum. This is right. Think about it. Very often when you have a collision, something bounces backwards. You really have to be good at this. You have to constantly be thinking about this. What's another name for change in momentum of the ball? What was another name for this parameter, change in momentum?
Average work.
Started with an I, but the letter was J.
Impulse.
Impulse. Okay. John, what letter do you guys use?
You just say integral F.
Okay, yeah, okay, that's cool. All right. Okay, oh, this was part D. Part D was impulse. All right. E, average force. I want the average force on the ball. What am I supposed to do? You remember? Check the units. Is it delta P times T or is it delta P over T? What's it got to be? Check the units.
Over T.
Over T, because I need meters per second squared, right? So it's going to be delta P of the ball, because I want on the ball, right? If we want to be on the ball, we need the momentum of the ball over delta T. I know it seems silly, but I think doing one of these problems with numbers, you can learn a lot, right? So what do we get out of this? It's 0.75 div, what was the collision time? 0.05. That's pretty typical, right? Where you have a very small collision time. Now look at this. I got 15 newtons. Is that correct? Is that what you got? Is that correct? What's missing?
The sign.
The
Direction.
vector, yeah. Okay, and I'm just, because, right, again, I know I'm being a dick here, but we got to get these vector symbols right. And so I'm trying to bust your chops on this first problem, because this entire chapter, we've got to get this right, okay? Sorry if I'm, harassing you about I hats and minus signs, but I got to do it. Wait a minute. Part F. What's the force on the Earth during the collision?
Negative that.
Negative of that, right? The Earth exerts a 15 Newton force that way on the ball. By Newton's third law, the ball exerts a 15 Newton force that way on the Earth. Think about it. The wall had to push the ball that way. Well, that means the ball was pushing the Earth this way. Why do we not notice the Earth move? It's just a little bigger than 75 grams. All right. You got it. What do you think? So there's a hidden Newton's third law in every momentum problem. Okay, look at part G. Let's figure out the change in the Earth's velocity. Okay, just for fun. These are the things physicists think are fun. Okay, how do I get the change in the Earth's velocity? How would you do it?
It's a final equation.
Okay, and do what? What equation can I write? You said I have to use force on Earth. How does that relate to delta V of the Earth? How does force relate to momentum? It's what over what?
Change P over change.
Delta P over delta T. Do you see the delta V hidden inside there? What's momentum?
That's a velocity.
So what's change in momentum? Mass times delta V. In this case, we can factor out the mass because the ball is not changing mass. In a rocket ship, where the fuel is being squirted out the back, the mass would change, and this wouldn't be true. We'll look at that at the very end of the semester, or at the end of the chapter. So let's rearrange this. Just for kicks. We've got all our numbers. It was what? 15 newtons I had, negative 15 newtons I had. Delta T was, I think, 50 milliseconds. And the mass of the Earth, what is that? 6 times 10 to the 24, is that what I said to use? Okay. All right. Oh my gosh. Well, do you agree the change is somewhere around 10 to the negative 24th? If we just look at the numbers, all these constants, let's get the actual thing because you guys care. For me, just see the 10 to the minus 24th is all I need to know. That means tiny. Negative 15 times 0.05 divided by 6 EE 24. So negative 1 times. What are the units of this crap? Meters per second. It's got to match up to velocity. We could check that. It looks like it works out. So the Earth is not going to change much, right? For reference, a hydrogen atom is about 10 to the minus 10 meters. A hydrogen nucleus is about 10 to the minus 15 meters. So this is about 1,000,000 times smaller than that every second. So this would cross that you would, it's so absurdly small. Are we good on that? Have you guys ever heard that one about everybody go to the North Pole and jump? How much will the Earth change? Have you heard this? Oh, maybe that's just an old physics joke. Let me put it this way. Look at problem 33. I'm sorry, not page 33, 9.3. If you're, I'm spaced out up here, I guess, yeah. If you are curious, if everybody went to the North Pole and jumped, and everybody was an elite athletic vertical jumper, and everybody had 100 kilogram mass, you could show what the Earth's speed would be after everybody jumps. So if you're curious, do that problem on your own, right? And unusual, does anybody happen to know who Muggsy Bogues was, other than me? Do you know, Don? Yeah. Okay. So this is an old basketball player. Anyways, all right. Yeah. Let's go back here and see if there's anything else I want to say about this. I don't know. Questions from the galley here. Any questions? Is this making some sense? This is super slow, but getting all the units and minus signs right. All right. Do that. 9.2 is a good problem that's a little bit, it's a variation on this one. So if you want some more practice, I noticed at the bottom of page 31, I say 9.2 and also 9.43 and a half. If you want, let's just skim 9.43 and a half really quick. Oh, that's outdated. I think it's page 51. I need to update that. 9.43 and a half no longer exists. Sorry, go to page 51 and look at 9.48. If you look at 9.48 in your workbook, imagine you were doing a lab like our first lab where you did tracker, right? And imagine, could you imagine making a plot of y versus time for a ball as it's bouncing around? You could then take these same ideas that we did up here on the board where we use momentum and time. The idea is you could get velocity off the plot to figure out the momentum just before and just after the collision. You can look at the portion of the graph which is concave up. That must be the time of the collision. And you could do all of these same types of calculations for real world objects from video capture. Got it? That's all I wanted to point out. This has a practical use. All right. That's about all I'm going to say about impulse in this class, other than when we do coding. We'll come back to that when we do coding. So we'll do this a lot in coding. Now I want to do problem 9.4. So let's look at 9.4, page 33. 9.4, page 33. I'll raise the board. You can start skimming it over. This is exactly the demo we were doing earlier with the two carts hitting each other on a track. Now, okay, we've got an object M1 and it's going to collide with that stationary mass. It's literally these carts that we were looking at right here. So we have one that's sitting there and one smashes into it, that kind of thing. Okay. Let me get on the board. M1. Notice there's always an initial and a final picture in these, or a before and an after, or stage one and stage two, however you want to describe it. So even though these wheels are present, right, that's basically just a technique we use to get rid of the friction. The wheels have negligible energy. We'll learn about that later. I think M2 is initially at rest. Afterwards, they collide. Let's assume V1 still keeps going this way. And V2 is non-zero. All right. We're going to try and analyze this problem. Now, I have a step-by-step method shown on the previous page at the bottom, but let's do that as a summary afterwards. I'm just going to walk you through this one and do it with you, and then I'll address some of the weird tricks that could happen. So let's start simple and just start with this problem. Okay, in this case, we're going to use conservation of momentum to determine the final speed of M1. All right. So conservation of momentum what is that equation? Do you remember? When we have two objects, do you remember what I said we could write down?
M1,
Yeah.
V1 initial.
All right.
plus-
I'm on it from there. You got it. That's the one I was talking about. That big long one. You know what I'm saying? Yeah, nice. In this case, it's usually good to plug in anything that's zero. Do you see anything that's zero in that equation?
V2 initial.
V2 initial, right? It's good to plug in anything that's zero before we get started. All right. Next. What, do we know numbers for any of these or not?
No,
Okay, so, okay, so we're trying to do it algebraically. Got it. Okay, so here's one of the things that's tricky about this. Let me show you this step. So we get numbers in part B. We could do this in one of two ways here, right? This is a vector equation. I could just stick on an I hat here, right? Like that. The other thing that I could do is, if I have a vector equation, I could say this is valid for the x components, and that's what I'm going to choose to do in this case. I'm going to stick on that third subscript. Subscripts are your friend in this section. Now, to be clear, this is exactly the same thing as saying, let's just look at the I hat parts. Do you agree? And now we want to be careful. When I plug in here, V1 initial X, is it positive V1 initial or is it negative V1 initial according to this picture? What is our default coordinate system? Unless otherwise specified, we assume that's a positive. So I would actually write this as M V1 initial. In this case, notice we've gone from having the vector to only looking to the X components to having the speed. This is the speed. Notice this is subtle, isn't it? These are all speeds. And that's why I took this extra effort of drawing the vectors, then saying the X components, then doing this. So far, so good on that? This one. Because everything's positive, hopefully you agree. We can now write V1 initial, V2, V1 final, V2 final, all are speeds, not velocities anymore. These are speeds. So, what were we looking for?
V1 final.
Trying to find M1 or V1. Final speed of M1. Okay, so V1 final. So solve this for V1 final. Go. Oops, this is supposed to be M1, isn't it? Maybe I'll divide everything by M1. Kind of handy because it cancels out this and this. And now I can see Is that what you got? V1 final equals V1 initial minus some other crap. So let's think. Does this make sense? Should V1 get faster or slower when it hits this object? Do you think mass 1 should speed up or slow down when it smashes into a stationary thing? So it's V1 minus a little bit. Looks pretty reasonable, right? Okay. Now we've got some numbers, right? Oh, read B carefully. Now we've got numbers, and instead of getting the speed, we're supposed to get the velocity of M1. Let's see what happens. Okay. Maybe I need space. I can't have that there. So in this case, what was V1 initial? 6. M1 is 0.5, M2 is 1. I'm going to run out of room. V2 final is 3.8 meters per second. Let's see what we get. We get 6 minus what? 2 times 3.8. I got negative 1.6 for this speed. Yikes. Who feels uncomfortable with that? A negative speed. Here's the trick. In our picture, we drew this as a speed to the right. If we get a negative answer, that's fine. It just means it's this speed to the left. Now, in general, I want you to listen very carefully to the way I say this. So the way I'm about to say this is true for every problem, not just this one. If you get a negative answer, the direction is opposite the way you drew it. As Don likes to say, opposite the direction drawn. Now let me go through this again. I chose to take a guess and assume this thing would go to the right for this problem. Because I got a negative number for that, that's fine. It just means opposite my choice. It's not always to the left. It's opposite your choice. If I chose to draw it to the left and got a negative answer, then it would be to the right. Everybody cool with that? If you get that, this part is not too bad. If you screw that up, you're going to be miserable for a couple of semesters. All right. So what was our point of all this? Oh, V1 final vector is equal to 1.6 meters per second. That's the speed. But the direction is negative I hat, opposite the direction drawn. Anything else you want to say about that, Tom? This is used not just in momentum. We use this all the time in civil engineering when we're building a bridge, whether you want to find out if something's in compression or under tension. It may show up at other times that I'm just going to stop talking. Okay. All right, you'll know what I mean later. Determine the change in energy in the collision. Okay, so, all right. Before we go on, any questions on B? That was a big deal. Okay, part C, change in energy. Well, what types of energy do you see here? Kinetic. So let's do this. Oh, come on. This thing battery dying? Okay. Part C was change in energy. And specifically, I guess, what did I say there? Did I say percent change or just change? Okay, change in energy. So K initial and K final, minus that, will equal the change in energy. That's what we're looking for, right? Do you agree I don't have to worry about gravitational energy for this problem? Everything's level. We don't have anything going up or down, so I don't have to worry about that. There's no springs. Okay, we don't have to worry about work done by friction because these things have the little wheels. All right. So in this case, There's the final energy. I need to subtract off. Do I need the second term here or not?
No,
No, why not?
because it's 0.
Yeah, so I'm just gonna put a little comment there. B2 initial was 0, that's why we don't have to include that term. In this case, I could factor out a 1/2 or whatever. Let's just punch in some numbers and get it done. All right. So go ahead and take the time to punch in the numbers. And if you recall, what was it? M1 was 0.5. I'm going to stop writing the sig figs because I'm really lazy right now. And what do we say? V1 initial was 6. V2 final was 3.8. Those are speeds. What was that other one? V1 final speed was actually only 1.6. Agreed? The minus sign had to do with the direction. Okay. When we crank this out, punch in some numbers really quick. 0.5 times 0.5 times 1.6 squared. 0.64. What are the units for energy? Joules, right? Check. Kilogram times a meter per second times a meter per second. That's a kilogram. Meter per second squared times a meter. This is an mg, that's a newtons, times a meter. It's a joule. Next term, 0.5 times 1 times 3.8 x squared. What was this? 0.5 times 0.5 times 36. And there's something hopefully we see out of this. I wouldn't be wasting my time with this if I didn't think there was a reason. You know what? I don't like to plug in numbers. What do we get? So we get 7.86 minus 9 negative 1.14 joules. Okay, did you gain or lose energy? Lost energy. When you have a collision, usually you lose energy. Okay? And more on this in a minute, but I just wanted to point out this is a typical collision. We lost a little bit of energy. Okay. What else? Oh, where does that energy go? Whoops. Oh, I've got the back of your head right now. Sorry. Yeah, sorry about that. Sound. Some energy is lost to sound. We could do this experiment, right? It's basically this one. Thanks, man. So the second one was twice as big. That's right there. The cart is 500 and this is 500. So this is approximately the same mass as used in the problem. This is the light one, 500, right? So it's going to be something like this. Huh. Maybe I do a little bit more. This one's just, maybe there's too much friction in these wheels or something, right? Should actually be moving afterwards. It's just really small. I can't wait. All right, there. Did you see it go backwards a little bit?
Yeah.
All right, so we're kind of seeing this thing. So we do hear a sound, right? That's not most of the lost energy though. Heat. When you hit these things, this is what happens, right? If you just slap your hands together over, we hear that sound, but we also feel your hands getting warm, right? What you're doing is you're taking macroscopic kinetic energy, the blocks that you can see moving, and it changes to microscopic, meaning the energy of the molecules wiggling inside. That's a complicated thing. We'll talk about that more when we get to 162. All right. All right. Finally, I want to say one more thing here that's a subtlety. During this collision, I want to point out that I did something that our derivation did not strictly apply to. When we did our derivation for conservation momentum, we said these things were in outer space, far away from everything else. And they were the only two forces in the universe, right? 1 on 2 and 2 on 1. Are there other forces acting on these blocks? Yeah, what are they? Gravity and? Okay, there's a little bit of friction. Let's ignore the friction for now, even though it's obviously not negligible. Normal force. What's true about the gravity or the weight and the normal force for each of these blocks? They balance. So what's the net external force? Zero. And that's why we can still do this. Anytime you have a net external force of 0, conservation of momentum is valid. Got that? I'm going to summarize this in a minute, but that's a big deal. Even more, anytime it's approximately valid. So usually this is true when the collision time is hella short. If you have collisions that are extremely short, like remember the bouncy ball hitting the cliff and the collision time was 50 milliseconds? Gravity was a non-negligible external force. However, because the collision time was so short, I lied and didn't talk about it at all. But when you think about that, during 50 milliseconds, gravity is not going to change the trajectory of the ball that much. So typically, as long as your collision time is super short, or as long as your external forces are balanced, we can do this thing that we just did called conservation of momentum. Got that? Yeah, so it's kind of important to know when you can actually do these things. Let's go through our problem-solving strategy at the bottom of page 32 now, okay? So let's read the bottom of page 32 together. Maybe I'll get some space on a board here. We've gotten so many tools in our toolbox from physics at this point. It's important to know when we can use these tools. When is it appropriate to use kinematics? When is it appropriate to use momentum or forces, etc., right? There's all these conditions that apply, and we have to make sure it's appropriate to use a physical law or a conservation law before using it. Step 1. Okay, so this is your conservation of momentum checklist. Before you use it, is it okay to use it? Are F external net approximately equal to 0? Are the external forces net 0? Or is delta T so short our result is approximately valid? If we don't check that before we do the job, we might have done all this work for nothing. Okay? Next, get a new marker, because that one's driving me nuts. Oh, that's better. Draw a before and an after picture, right? Or stage 1 and stage 2. Yep. What's that? Oh, yeah, sorry. Thank you for mentioning that. Appreciate it, Jules. Sorry about that. Okay, so is it okay to use it? Basically, is the external force 0 or is delta T super short? Draw a before and an after. Something I want to emphasize that's subtle. If you are unsure of object direction pick something and do it. Pick a direction and solve the damn problem. Okay. And then there's some words, blah, blah, blah. But basically, if final answer for whatever, a speed is negative, the key words were opposite direction drawn. Right? So just because we don't know which way something goes doesn't mean we can't get the problem done. Just do the damn problem, and then at the end, think about your minus signs. Okay? We can then, right, I'm going to enhance that version we had earlier. This is all there for you. Remember that any of these could be plus or minus based off your pictures. So we have to include plus or minus signs. Basically, there's an implied I hat. Remember when we did that in kinematics? So all of these terms could be plus or minus on those, right? Right. I have a pet peeve. When we get to two-dimensional problems, right? Let's say we have V1 final. And there's some angle here, theta. I want to point out that V1 final x is equal to V1 final cosine theta. It is not equal to V1 final x cosine theta. Okay? This drives me nuts and makes me want to puke. When I see somebody write V1 final x cosine theta, you'll know it if I'm grading a test and start puking. That's a joke, right? But basically, watch out for this. I want you to use the terms correctly, right? V1 final x is okay, V1 final cosine theta, but don't do both. That's like double counting the angle. You know what I'm saying? Just want, it's like double counting gravity and potential energy. It's just wrong. Okay. Okay. 4. In general, when you have a collision, you lose energy. Most of the time in the real world, when you have a collision, you lose energy. Some special collisions lose negligible energy. Like if these magnets were stronger, I'll soup them up in a minute. But right, what if you have a spring between the two blocks? This is why some cars will have springs on their bumpers, right? So your bumper can compress and then re-expand without ruining the car. Okay, so sometimes there's key words. Usually these are collisions with springs or other conservative forces, magnets. There's a weird one we'll see where actually there's gravity can be used in a collision. If you see the word elastic, that's another key word. If you see the word elastic, this is how I remember this. For me, this was kind of tricky when I started. Springs conserve energy, right? Springs are stretchy and bouncy. Stretchy, bouncy, elastic, stretchy, bouncy. Somehow that works for me. Springs conserve energy, elastic, stretchy things conserve energy. Then there's inelastic, which is every other type of collision, which is most collisions, which means losing energy. Right? Notice if you have energy conserved you get a similar equation with all the velocities squared, right? Because the 1/2s are going to drop out. You get 1/2 mv squared. 1/2 mv squared, 1/2 mv squared. So it's a slightly different calculation because all the plus minuses drop out in the squareds and all the halves drop out. But all right. Then read and solve for something. What do you think? Should we just call it a day and say we're done with chapter 9? You guys would be toast. All right. I've got one more conceptual question before we go to the break. I want to hit this right now, but any questions about the strategy before we do that? I know you're time for break. I'm going to get you there. All right. Look at 9.5. School bus collides with an insect. It's a normal insect. It's not a 10-ton butterfly, as Nick Butler remembers. That was a physics question once. 10-ton butterfly hits a school bus. Gee, I wonder who wrote that one. Take a second. Talk to your neighbor on that. Try not to look at the answer, even though I know you can. Talk to your neighbor on it. See what you think. See what they think. And then we'll take our break, I promise.
Force isn't. I don't think force is the one that has more mass. The books have a greater has a smaller change in velocity or change in momentum, but the force of pressure is the same. With it stays in the tissue. It's like which comes like in regulation. Right. Mass has to do with momentum. Force is like say what Joshua was saying. The ball it wasn't enacting the same amount of force on the earth as the earth was ball. But the change in momentum is greater on the ball, the earth, because the earth is going with mass. So I think what is here during the collision there's larger force. I'm pretty sure it's the same for both of them. The ball like exert like that. Right.
All right. Let's take a vote here. Which one's going to have more force on it, the bus or the bug? Which one has more force acting on it?
But they're both the same.
The same because of what? Newton's third law. It doesn't matter on the masses. Remember this?
I got half.
Okay.
Half of it.
This is why I wanted to do it to trick you, right? Force 1 on 2 magnitude equals force 2 on 1. Remember, the vectors are equal and opposite. So the vectors have that extra minus sign in it, right? But they should have the same force. However, what's the next part? Which one has the larger change in momentum?
The bug. Right. It is the bug. Has to be.
Which one has the larger change in momentum? If they have the same force,
They have the
same delta P. I was trying to trick you.
Okay.
Because delta P,
It's directly connected.
I should be careful here. How about I say it like this? Do you agree the force is delta P over time? So the changes are equal and opposite, but the magnitudes of the change are the same. So they have the same change in momentum. Now here's the deal. Clearly the bug has a larger change in velocity, but the momentum, right, is mass times velocity. So just because the bug is going to change velocity a lot more, when you multiply by its tiny mass, it should exactly balance the change in momentum.
Okay.
You see what I'm saying?
Yeah.
Clearly, okay, let's keep going. Which object has the larger acceleration? That's the bug. The bus, think about this. When a bus hits a bug, does its speed change much at all?
No.
No. However, the insect was sitting here and now it's going 80 miles an hour because you're driving these kids in a school bus at 80 miles an hour. Duh. Whatever. So clearly, I'm going to say it like this. Smaller mass has more A. Think about it like this. F 1 on 2 vector equals negative F 2 on 1, right? Well, let's just say the bus is number 1. There's mass 1. There's acceleration 1, right? Equals, come on now, negative sign. There's mass 1. There's acceleration 1. I think even though it's cheesy, I think that visual really helps me understand it. If one object's got a big mass, it has a negligible acceleration, and vice versa. Tiny mass, huge acceleration. Yes.
Shouldn't it be mass 2 acceleration 2?
Yes, it should, and I screwed up. Thank you. Oh man, now I gotta get in here again. Now that's correct. Okay, there we go. Thank you. Thank you. Bad. My bad. Oh, shoot. What else is wrong here? This is on 2, but I wrote ones. Clearly that's an error. Do you agree? So I switched both of my, so this should be, let's just get this right. This would be the force of 2 on 1. And this one would be the force of 1 on 2. And now I think this makes sense. Sorry, I did that wrong. Thank you for catching that. That was good. Does that make sense? All right, now let's take our break. You guys made it 12:17. That's like the longest I went before a break, I think. I appreciate that extra time. Hopefully that kind of locks in some of the things we were talking about. We're just going to do more practice when you get back. I've got 12:16 up here on this clock. All right, so it's time to get back into it. At this point, we're ready to do as many practice problems as we can. Now, in my opinion, I think it's most useful to you if I show you as many setups as possible, knowing that you got the solutions and the full answers. So I think what I would like to do is try and do as many setups as possible, because I know there's not infinite time in this class. The next class, we're moving on to center of mass. So before we do as many possible problems as possible, look at page 34. And I want to tell you about the different types of problems we have to work on. We've got 1, 2, 3, 4, 5 different types of problems that use the same techniques. Each one of these problems has subtle differences. Basically, each one of these types of problems has something you're supposed to know or memorize to help you do the problem. Sort of like when a ball reaches max height, you know V final Y equals 0. Similarly, if you have a perfectly inelastic collision, that means the two objects stick together. You're supposed to have that memorized on test day for test 3, not test 2. If it says elastic, I'm reading off page 34, right? And maybe I'll write this up. So perfectly, well, let's do this. Types of collisions. There's perfectly inelastic. Now remember, and I'll also write elastic here. For me, it helps to first remember that elastic is bouncy like a spring. E initial equals E final. Okay. If it's perfectly inelastic, that means it's the opposite of bouncy. The objects stick together. After the collision. So they form one object. That means there's only one V final. That's the trick on this one. Only one V final term. Okay. Now there's inelastic. Inelastic is different from perfectly inelastic or elastic. This is like, what problem was that? The first one we did, it was 9.4. Remember the problem we did, 9.4 with the carts? You have an object here, hitting one here, and then they both move off. So you lose some energy, right? And maybe this one's moving too, I don't know, it doesn't matter. But there's some sort of collision with energy loss, but they don't stick together. This is most collisions in the real world, right? Most of the time they don't conserve energy. Most of the time they don't stick together. Then there's explosions. A typical explosion is like a perfectly inelastic in reverse. Now think about this. Imagine you have a perfectly inelastic collision. Like imagine somebody throws a pizza at my face and it just wraps around my face and stays on there. That sounds good. If you played the video backwards, the pizza and my face would be one object and then they would separate. That's like an explosion, right? Or if you have a bomb, it starts as one piece and splits into fragments. Okay, so that's the opposite of perfectly inelastic. So we can not only handle collisions, we can handle explosions. And finally, there's a weird one that only physicists seem to care about. An elastic explosion. This is pretty difficult to achieve, but it can be achieved if you take a spring and put it between two objects and allow them to fly out. So that's usually what I think of. Where you have it before like this, and then afterwards the spring kind of falls down and the two blocks go flying out. So you used a spring which conserves energy to cause the explosion. There's one other case that makes me think about it. There's a problem you'll see where there's like an ice cube on a track on an ice rink. Only a physicist would make this problem. This is before. And then afterwards, the track goes this way and the ice cube goes that way. In this case, if there's negligible friction, you can think of this as one object exploding into two pieces and conserving energy. Again, if friction is negligible. So these are the types of variations. Now, to be clear, every single one of these problems uses P initial equals P final. Hopefully that's on the screen, or is it off? Okay, thanks. Just barely?
Yeah.
So they all use conservation of momentum. Sometimes they use conservation of energy. Most times they don't. Sometimes they group together and there's only one. Okay, these are the variations that we're going to do. And so something's going to be on your test out of all this crap. Because 9.6 and 9.7 are pretty straightforward, I'm going to let you do those at home. All right. And you can see I've started filling those out for you. But for those problems, 9.6 and 9.7, they're like these problems here with these carts bouncing around. They could be elastic, right? By using these magnets on here, it's an elastic collision. They don't actually touch, so no energy is lost there. Obviously, there's some friction. Or you could have perfectly inelastic, where they collide and stick together, and those two problems help you look at that. And then you can see what should happen if you put different masses on here. One of my favorites, I'll just show you one case before moving on. If you have a really heavy object at rest, and you take a light one and smash into it, we see the light one goes backwards and the heavy one moves off. If we switch this, it's dramatic. Watch this. If we have a heavy object hitting a stationary light, that one goes flying off. Whoa, let me do that one more time so it's fully on the screen. You can see that one goes flying. So those are some interesting cases. Okay. I would like to do 9.12. Let's go right to 9.12. We haven't done a 2D example yet. Everything so far has been 1D. Let's do a 2D problem. Okay. 9.12. Two cars drive towards a junction. They collide. It says the collision is perfectly inelastic. All right, got it. So there's, I'll just have a red car and a blue car, it doesn't matter. They're going to collide and hit at this dot. And this angle is supposed to be 60 degrees, even though it's maybe not perfectly 60 degrees. And that should be a little bit more like this. That looks a little better. That's probably not 60 either, but it's closer. This one is labeled 1. This one is labeled 2. Car 2, M, okay, so this has mass M and speed V, and this is all before the collision. Car 2 has twice the mass. So this must be a Buick versus Ford Fiesta or something. Okay. After the collision, the cars move in unison with speed 0.441 V. So what does the after picture look like? What do you think the after picture looks like? Here's that dot where they collided. What do you think is going to happen? What should I draw?
Probably two pushing one.
What type of collision is this? Did it say?
Perfectly elastic.
Perfectly inelastic. How many objects should I have in the final picture? One. So there's going to be kind of this purple blob here. What's the mass? Yeah, because it's 1 plus 2. This is 3m. Which way do you think it's going? Point with your finger, everybody. Just show me. Which way do you think it's going? Okay. Do you think it's going straight up or straight to the right? Somewhere in between, right? Well, let me ask you this. We don't know these numbers. Do you think it's closer to this or closer to that? Or do you think it's exactly halfway in between? We don't know for sure, but you might think at a first guess, if this has twice the mass, well, we don't know the speed, it's not clear. You might think it kind of goes off this direction, agreed? We don't know that though. But that's probably what we're going to figure out. What are we supposed to figure out? Oh, determine the initial speed of car 2. Once we know that, we could then figure out the angle. So let's assume it goes off somewhere in between there. I'll call that, should I call that V final 1, V final 2? What do you think? That would just be final because there's only one of them. You see what I'm saying? What are we trying to find in this problem?
Initial speed of V2.
So we're looking for V2 initial. What coordinate system should we use for this one? How about a normal one? Right, let's use a normal coordinate system so we don't have to do any backward stuff, right? Okay. I'm going to write down conservation of momentum. Is it valid to use that here? What do you think? Are there external forces when we have these two cars collide?
They balance out.
They balance out, right? These cars are driving on a road, so there's a normal force. We're looking at a top view. So if I didn't say that, maybe I should mention this is a top view of the situation. Right? So there's weight going into the page and normal force coming out of the page. They're going to balance, just like the last problem. All right. So here's what I'm going to do. We only have one final. I'm going to split it into x's and y's. So remember, there's an implied I hat on all of these. There's an implied j hat on all of these. Is anything going to be negative in this problem, in this particular one? Is anything going to the left or down? No. So we don't really need to worry about this, right? So for this problem, you might gloss over this fact, but it's worth mentioning. Always double check if you need to worry about plus minus signs. Okay, what should I write for P1 initial X? Somebody tell me. P1 initial X.
M times V.
M times V times what? Is all of this V in the X?
Cosine of.
Cosine of. Good. Do you agree? It's got to have some kind of cosine, and we're not obvious whether it's 60 or not. Do you agree? So let's figure that out. If this angle is 60, what's this angle?
30.
That's 30. So then what's this angle down here?
30.
So do I use 60? Sure, but I'd have to use sine of 60 degrees or cosine of 30. Do you agree? One of these two angles. So now we have to take into account that angle somehow. Did that make sense? I'm going to use sine of 60 because I like to use the angle that was given in the problem if given a choice. And maybe I'll make this look a little bit more clear. I don't know how to make it look more clear. I'd have to label it somewhere else. Right? If we know that this angle is 60 degrees, That means this angle is also 60 degrees. And then I think you can see a little bit better. That's why I'm using sine of 60 up there. All right, how about P2, initial in the X?
0.
Okay. How do you know it's 0?
Because it's moving the one direction.
Yeah, there's no component X. There's no left or right to that. So that's a trick that sometimes we got to look for. What are we going to do for P final X?
3n times
3m times V final times what?
you don't know the angle.
Okay, so we better make one up. And then we could find the angle. Remember how I said we don't know the angle, but I bet we could find it? If you're wondering how you might go about finding that angle, well, let's see. In this case, do we know what V final is? Did the problem tell us what V final was?
It's just 0.441 of V.
Well, hey, look at this. Is it possible to figure out the angle? Yeah, let's do it. What drops out in this equation?
M.
M. And then when I plug in the V, you agree the V is also going to drop out? And I get sine 60 degrees equals 3 times 0.441 times cosine of some other angle phi. Now I know we don't necessarily need this angle, but since it's so easy, it's worth it to get it. So sine 60 divided by 3 divided by 0.441 equals cosine inverse of that answer. I got 49.1 degrees. Again, you could do some math and solve this. I'll assume it's good at 3 sig figs. I'm going to keep an extra one just in case we need that over here in this other equation. All right. Somebody else, he did that one. Somebody else do this one. What's P1 initial in the Y? P1, so what mass do I use? M. What speed do I use? The cosine of 60. Do I need to worry about any plus minus signs? Is it plus or minus? Plus, it's up. Next, P2 in the Y direction. Initial. What would that be? 2m times how much of this speed should I use? All of it. So I just write V2 initial equals P final in the Y. What's that going to be? What mass? 3m, because it's all of it. What speed should I use there?
0.441 V sine of.
Didn't you just do the last one?
Yeah.
I'm trying to get other people.
No one else is talking.
Yeah. What's that?
No one else is talking.
All right, I know. Times what? Finish it out. Go ahead.
Sine of 49.
Sine of phi, which we know phi, you said was what? 40 what? 49.11. This is when you want to use the extra digits, right? This is why I like that underline. Okay. At this point, what drops out? Wait, let's check the m's. The m's drop. Do the v's drop?
Oh, we're trying to solve the V.
We're looking for V2 initial. Notice the v's don't drop, so your final answer will be written in terms of one of the other v's. Now, I'm not trying to snow you. This is exam level difficulty. This is how I write these kinds of problems on a test. I usually use the masses as m's or multiples of m's, and the speeds as v or multiples of v. The reason I do that is it makes it pretty easy to do exam variations. It's not because it's the greatest way to do it. It's just, it makes it easier to write the exams, that's all. But now that you're kind of used to it, after half a problem, surely it's easy. Should we go ahead and finish this out now? Let's see what we get. B, what's cosine of 60? Right, sine of 30 is cosine of 60. This one, we're gonna have to plug in some numbers, do you agree? In the calculator, 3, this, that. I'm gonna crank it out in the calculator. So I need sine of that answer times 3 times 0.441. Whoa! Now I know why I used 0.441. I'll keep some extra digits there just so you can see it's not exactly 1. All right, at this point, it's pretty easy to solve for B2. Right? It's going to be, whoa, take a look. Well, I don't want to screw this up. Basically, it's 1.000V minus 0.500V. That's a half. Bring it to the other side. I'm going to divide it all by 2. So what do you get?
0.25.
Yeah. And now we can kind of get a feeling for how these collisions work. If we look at these things and kind of think back to what these are, this angle is drawn approximately to the scale. That was 49.1 degrees, right? And we can see that the initial speed of this one is a lot smaller. In particular, if we draw it to scale, it should be about that big. It should be about 1/4 of this, maybe even a little smaller. So 2 is like a big semi-truck, twice the mass, hitting a car. The car's going faster, but the truck's got more mass. And in the end, it looks like you get this weird angle here, right? Okay, cool. I don't know. Any questions on this? Yeah.
So we're talking about collisions. I have a question. That is, if an object's going, let's say it has a smaller mass than another object, right? That the object's going to collide with.
Yes.
Is it possible that with enough speed, the smaller object can survive intact by colliding with the bigger object?
That's a difficult question. It's going to depend on the objects, right?
Right.
Like imagine you take a bullet and shoot it at me. That bullet's moving really fast.
Right.
Oh, I wouldn't have to teach in grade anymore. Yeah.
No, but
No.
no, I was referring to like larger objects. Let's say a vehicle, like a small compact car versus like a truck or trailer, or like something like
Right, right. Basically, cars are designed to crumple, right? By
Right.
crumpling, why do they do that? When the car crumples, what happens to the collision time?
It extends.
And then you have less force, you're less likely to die.
Right.
Right? So now that doesn't mean there isn't maybe some situation that could be manufactured, but in general, I don't see, right, the indestructibility of the object usually being the goal here. When you have a collision, right, I guess one example might be a black box recorder on a flight, right? When the plane crashes, you want to make sure that thing survives the collision, agreed?
Yes.
So I don't know what they do to make sure that survives, but it's probably layers and layers of other stuff outside that does get destroyed so that one thing can survive. So I'm not sure if that answers your question, but I just know that in the interest of time, we're gonna have to move on, but yeah.
Yeah. Okay. I mean, it's,
Yeah, we could talk right afterwards too, because we've only got 20 minutes left or so, or 25. Good?
yeah,
All right,
Yes.
yeah. In general, what can you do? Conservation of momentum and figure it out for each case. So you know enough to figure it out on your own now. Isn't that cool? You
yeah.
could, right? You can take videos of objects, do conservation of momentum and see what happens to them. And you can see what the initial momentum and final momentum are. You get the initial energy and the final energy. You can do it. More when we're done. Okay. I got another one for you. Take a look at 9.13. We're done with this problem. I don't know what else we were supposed to do, but I think we got it. Weren't we supposed to get V2 initial? We got it. Look at this one. All right.
Oh, that's good.
Yeah. Can't see anything. This thing, screensaver is always turning on me. All right. So now I want to look at this problem here, 9.13. Take a second to read it. I'm going to erase the board. Still erasing if you're on Zoom there. Getting there. Okay, you take a tennis ball and you put it on top of a basketball. You got to drop it, right? So now if we want to see the result, you got to do the math. Come on, you know me. You got to do the math first. Check this one out. What number did I call this? 9.13. Thank you. The B-ball, tennis ball drop. So when you drop it, what's going to happen is the basketball is actually going to hit the ground. And in order to make this simple so that we can see it, the actual collision is a little bit more complex than this, but I want you to imagine I dropped the basketball just a millisecond before, right? And so the basketball is going to go down and then it's going to be bouncing back up and the tennis ball will be falling down. So to simplify the work, again, imagine the basketball has bounced up and the tennis ball is still falling, right? So like that, okay? So just before the basketball on its upward trajectory smashes into this, there we go. Okay, and to be clear, if we drop them from height h, I'm going to do a quick energy problem just so in the interest of time. If we take one ball here and it falls distance h, what's the initial energy? What type of energy does it have initially? mgh. And then down here at the bottom when it's moving, what type of energy does it have? Kinetic. What's the speed at impact?
The square root of 2gh.
V equals square root of 2gh. So just keep that in mind. The whole reason for mentioning this is the height at which the balls bounce. If I solve this for the height, right, you could say that the height is equal to v squared over 2g. Either way, notice that the height is proportional to the speed squared, or v is proportional to the square root of the height. Good. So now these things are going to bounce, and my claim is when they do that, the tennis ball should go upwards. We know this from experience. I'm going to call them 1 and 3, right? Because they have 3 mass and mass, sorry, this is mass m and this is mass 3. And that's why I'm calling them V1 and V3. Okay? You could call them 1 and 2 if you wanted, I don't care. Oh, in the book I called them 1 and 2, so maybe I should do that. Sorry about that. This is an elastic collision, is that correct? Oh, what are we assuming about the collision? All right, here's the deal. Let's talk about this really quick. Let me just zoom out. All right. When I have this basketball here and I'm going to bounce it, how could we tell if it's elastic or not? If it was perfectly elastic, how high would it bounce after the collision?
The exact amount. Or height.
Within rounding, it does, right? The whole point of a basketball is we don't want it to be a lot of work to have to bounce it. So we're going to say, even though, do you agree it is not elastic? It's approximately-ish elastic.
That's why you overinflated it? Or?
Exactly. If I had overinflated it even more, the more I overinflate it, the better it's going to bounce. So that's why it's overinflated. All right. So we're going to assume this is an elastic collision because we need to do a practice problem with elastic collisions. Got it? That's what we're doing here. Right? So we're going to assume elastic. What does elastic collision mean? Energy is conserved. So if we have an elastic collision, this is true. We have a collision. What's true for every collision? What's conserved for all collisions?
Well, that's
Okay. All right. So we can write down 2 equations for this problem. Notice if these are givens, we should be able to find out the 2 final speeds because we have 2 equations for elastic collisions. Does that make sense? So with normal collisions, basically you can find 1 parameter, a final speed or an angle or something. Here, well, actually with 2D collisions, you can get 2 things, right? Because there's an x equation and a y equation. All right, so in this case, let's write down conservation of momentum really quick. So I'm going to write m. Why did I put a negative sign for this one?
It's going down in our relative coordinate system.
We're assuming our standard coordinate system. Excellent. So this one would be negative mv. This one would be what?
3 MV.
Positive 3 mv. Then over here, they're both going upwards. What drops out? When I get all that together, what's left on this side? 2b or not 2b? That's the question. So dumb. All right. This is the momentum equation. So this is P initial equals P final. What symbol is implied on all of these? J hat, because we're doing it up and down. All right, good. Let's do the energy. What's the initial energy? 1/2 mv squared plus 1/2 3m v squared. Okay. 1/2 m. Whatever. When you're doing these, people, just be careful, right? The one thing sometimes people forget is they forget the number that's on the mass sitting out in front of them. You know what I'm saying? La 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 la. Losing my mind. What drops out in this equation?
The 1/2.
The 1/2. That's what I was saying earlier. You get these energy equations, the 1/2 usually drops out. What else drops out? So this is why I like to write them this way. They're also a little faster once you get used to it. Basically, you use one mass as a reference mass and all the others are multiples of it. What's left on this side then?
2b squared.
The 1/2's dropped.
Oh, 4b squared.
Yeah, 4b squared. Do you agree? You see it now? Yeah, yeah, okay. And then what's left on that side? How would you approach this? What are we trying to solve for? What were we looking for in this problem?
Speed of the balls.
The speed of the balls afterwards, right? So let's try and find V1 final, right? So if I want to, actually, let's find V2 final first, because that's the weird part. So if I want to find V2 final, what would you do? We've got two equations. How would you approach that? Let's say we're looking for V2 final. What would you do with these two equations? Just tell me. Algebra. What algebra step?
Set one side of either equation to be one final and substitute it to the other.
Yeah, that's what I meant. I'm sorry. Maybe you guys were thinking I meant something more complex than that. That's exactly what I meant. Do you agree this one's easy to solve for V1 final? Sorry about that, if I confused you. We could take that and shove it in right here. And then, once we do that, do you agree only V2 finals will exist? It's a little weird because you have to remember V is technically something that we were given in the problem. So V is a known. So that's why this looks a little bit weird. You're like, there's 3 variables here. No, technically there's 2 variables and 1 known, or basically 2 unknowns and 1 known. V is supposed to be known. Okay, let's do it. Looks ugly, doesn't it? Welcome to elastic collisions. Now, I guess I'm just going to go FOIL. Let's do it. When I FOIL this, what am I going to get? Oh man, or square it, right? I'll get, how about plus 9 V2 final squared minus 2 times the cross term, or plus 2 times the cross term. There's a minus sign there.
Minus 12.
Something.
12 V V2F. And then that's just this term. I got to remember this one. Woo! Let's make sure we got that. First term squared, second term squared. This is -6 V V2 final, double it, -12 V2 final, V, and then this one. Can we clean that up a little bit?
Oh, we can cancel out.
Isn't that cool? That drops out. And now I get 0 equals, I'm just going to write this like this, 12 V2 final squared minus 12 V V2 final. What algebra technique might we do next? Yeah, factor or whatever you want to call it, distribute. Remember that trick I said was going to come up in one problem this chapter? And I said, in fact, this is that problem. That's what we get. And now just so that the algebra is on one page. Okay, I'm going to bring that up here. We say that 0 is equal to 12 V2 final times V2 final minus V. What are the possible solutions? Give me both.
Final to 0. V2 final equals V.
Which one of these do you think is correct? I'm going to go back to the picture here. Oops. Jules, can they still see that a little bit? All right. What is more realistic? Do we think the basketball will hit the tennis ball and lose no speed, or do we think it will stop? Which is more realistic? Right? It was initially moving upwards with speed V. You're telling me one of the possible solutions is it will continue at speed V. Is that realistic?
No.
When it hits something, doesn't it have to slow down?
Yes.
What is the only reasonable solution? The basketball stops moving. And if the basketball stops moving, what happens to the tennis ball?
It continues upwards.
How fast? It's going to reverse direction and go twice as fast. How high will it go? If it goes twice as fast, it will go 4 times as high. What? Let's do it. Isn't that cool? Let's do it over here. So now, how high is the ceiling? About a 1/4 of the way to the ceiling, right? Jules, am I on? Yeah, you're fine. Okay, can you come over here and help me? I want you to put the ball on top. And then, yeah, don't get hit in the face. So maybe push your glasses. Okay, try to notice the balance on there. Just put it right on the holder. I'm gonna tell you what, I got it. Put it on there and I'll balance it. Ready? Not quite, but this is not perfectly elastic, right? So maybe you've seen these with the bouncy balls, but the idea is you can launch it. March Madness in the classroom. All right, it's kind of fun. Go drop a right. Inflate your basketballs at home and do this. Okay.
Mammal March Madness.
Yeah, this is March Momentum Madness. It's like the worst. Come on, camera, come back to me. There we go. All right. Weird. We're starting to run out of time. There's never enough time. Check out this one right here on the desk here. Let me get this right here, just for fun. Let's have a couple of these demos because Angus took the time. I maybe didn't time manage very well today. All right. Whoops. Now, I don't know if you can see this very well. But I got these 2 spheres, and when I drop them, right, 2 spheres, notice one's very bouncy and one's not. What I'm going to do is I'm going to release this one from rest. Didn't knock this board over. Now I'm going to do the other one. Oh, it's just enough to knock this over. Which one was able to knock it over? The bouncy one or the not bouncy one? The bouncy one. Why is that? Explain.
All conserves movement.
What exerts a force on the board to make it tip over? The ball exerts a force on the board. Do you agree that the board also exerts a force on the ball?
Yes.
On which ball will the board have to exert a larger force? The bouncy one, because it doesn't just stop its momentum, it has to reverse it. That's a bigger change. That's why when the, let's see, is this the bouncy? Oh, this is not the bouncy, right? So this should not knock it over, right? It impacts it, the board stops momentum, that's a force. It's not quite enough to tip it over. But if it has to reverse the momentum, it's just enough to knock this board over, right? So again, if something is reversing something's momentum, there's a larger change than just stopping its momentum. Got that? So when you're driving, right, if you had to choose between running into a tree versus I don't know, another person, you might want to actually run into the tree because it might actually take a lot longer to stop. Or maybe, I don't know. You make your decision when you're crashing. All right. Try not to crash. How about that? All right, we got another one over here.
What if you crash and hit both?
What's that? Then yeah, just do a glancing collision. Will you? Try not to kill people. How about that? Let's do that today. All right, so let me get over here to this one. I know, right? Physicists are off.
Oh, you also kill people versus wheels.
Okay. You see that all right, Jules?
Yes.
Okay.
Which one would you choose?
You know the Newton's cradle, right? So this is kind of a fun one, but it's a bit more complicated. It's a fun demo. But right, the idea, the classic thing that teachers say is, well, these collisions of steel on steel actually are very elastic. So steel will not waste much energy when it hits another piece of steel. Okay, that's what we're basing this demonstration on. We're assuming these collisions are actually perfectly elastic. So when I raise one ball, we see one go up on the other side. Now it turns out the little ones tend to work a little bit better because there's actually some issues with shockwave time propagation, I think, or something more complicated. But the idea is if I raise two of these, the only way to conserve energy and momentum is if two of them go up on the other side, right? Now, if you read in the literature or you read the solution on this problem, you'll see there's some subtle problems with what I just said. So I don't want to spend all day on it, but this is pretty cool. What if I raise 4 on one side? How many should go up on the other?
4.
It's cool. Or if you do, right, 2 and 1, that's one of my favorites. Whatever. So you guys can do this at home with your, but again, these little ones tend to work better. I think it's because the time for the shockwave to propagate is small. So if you're interested in that, you can read about that in the subtleties because everybody wants to learn about that. It's 9.14. I say fun demo, skip that problem because I don't really, I'm just going to leave it at that. What else? Oh my gosh, there's never enough time. Well, we'll just have to stop there. That's it. Maybe I'll try and do a couple more. But yeah, make sure, let me put it this way. Put a star next to 9.15, 9.17, 9. I'm going to write these on the board. Let's do that. Just, I want to make sure you get to these because you, right, in class, there's never enough time. There never will be. So let me just mention some problems I feel like you really have to do to understand these. So 9.15, 17.
Those 2 snakes.
I like 17 and a half a lot.
Aliens. Through
And
18. 17 and a half.
I like 22 and 23. Obviously, I've written up a bunch of problems. I'm just looking at ones right now. I really loved 9.18 myself, but I think you would be an insane fool to try and approach that one. I was imagining 2 aliens playing catch on hovercrafts in space. It's really cool.
Like how you did it, the demo?
What's that? Yeah, but imagine how long could you play catch? Because each time you throw, you recoil. Each time you catch, you recoil. So my question is, at some point, you're going to be moving backwards so fast, your throw is never going to reach the other person. How many times can you play catch in space? That's that question. So just read the answer instead of doing it if you're crazy. I like 9.11 as well.
That is great.
That's usually one I do. And to be fair, we probably got to do, I'm going to say 8 and 9 as well. If you can do all of those, man, you're gonna be a monster. All right, that's pretty good. Yeah, but I could make you do all of them, right? I love them all, and the thing is you need to do at least some subset, and I feel like if you do these, at the bare minimum, you'll have seen most of the types of collisions, okay? And like I said, we gotta move on to center mass next time, so you gotta look at some of these. Hopefully there'll be more time to do more later, if we could finish center mass early. Okay, that's really it. Get out of here. Thanks for the extra time. Sorry I wasted your time.
Mr. Georgeson,
Yeah,
if I can ask about that one
can I
question.
end the live stream right now?
Sure.
Okay.